right, then I think we will get going.
All right. Well, thank you, everyone. Good day. Welcome to the Motor Control Trainer and Flip Classroom webinar we're putting on today through the Create Center with our presenter, Jim Pytel. I am Andy McMahon from Central Carolina Community College. I'm the chair for the Department of Sustainability at the college, and I am also a co-principal investigator for CREATE, the Center of Renewable Energy Advanced Technological Education. CREATE's mission is to create and advance the field of renewable energy by supporting two-year technical colleges in the fields of renewable energy so that we can grow, we can help to support those industries grow. If you'd like more information about the Create Center, you can visit our website at createenergy.org, see some of the other past webinars we've created, and also look at some of the other content that we have available for instructors. Before we get started with today's webinar, I just want to make a quick pitch for our next webinar in the series of teaching tricks, tips, and ideas. We're going to have a presentation by Eric Nispel regarding the heat of biofuel combustion. So please, if you are able to, join us on March 4th for that. If you'd like to sign up for that, you can contact Gabrielle Temple. Her contact information is on this slide. So for today's presentation, I'm going to go ahead and introduce our presenter, Jim Pytel. Jim is an instructor at Columbia Gorge Community College in the Dalles, Oregon. Prior to working at the college, Jim served as a captain of the 4th Infantry Division at Fort Carson in Colorado. He worked as an applications engineer specialist working in interferometry at ADE Semiconductors, and was also the lead technician for the GE wind farm in Klondike. So that's where his application from the electrical engineering kind of met with his expertise in wind turbine technician training. And then in 2009, as part of a Department of Labor grant, Jim started to teach at Columbia Gorge Community College and has been there ever since. Jim teaches, he's the electromechanical technology instructor. He teaches electrical circuitry analysis, hydraulics and pneumatics, motors and controls, digital electronic courses, and power generation and transmission. So all these types of courses that we're going to, all these courses that he's teaches, in addition to his typical coursework at the college, has done a phenomenal job of developing and curating a series of online lectures funded through the National Science Foundation's Division of Advanced Technological Education, where he has put a lot of his lecture components online to help facilitate students doing online lecture learning and then being able to come to the classroom. But I don't want to step on his presentation. I'm sure he will address that today. Otherwise, Jim, I also want to say that you have a great presence on YouTube with your BigBadTech Channel, which I think is how you distribute a lot of these lectures you've created. And it's quite impressive if you haven't seen Jim's collection of lecture videos. They are informative, humorous, and certainly bring his own personal style to the table when he does them. So with that, I'm going to pass it off to Jim and let him take over for the webinar today. Thanks, Jim.
All right, folks, welcome. As Andy said, Jim Pytel, Columbia Gorge Community College. So I'm going to switch over to, I'm going to share a screen real quick here. And as Andy mentioned, this is the YouTube channel I've been publishing all my content on. If I was to give this presentation 3 or 4 years ago, I'd have to introduce everybody to what is a hybrid learning structure, what is a flipped classroom approach. But now with COVID having happened, what I feel is everyone's aware of this methodology now. Basically, there are online content. A student is assigned a certain quantity of lectures throughout a week. Perhaps a worksheet is given with it, and then they actually show up. So any time in the class, rather than sitting down and looking at a whiteboard, is actually set in front of actual equipment and using hands-on environment. So I found this technique to be extremely effective. The students enjoy it. I enjoy it. It's a great way of getting more exposure to real-world equipment and instrumentation. As you can see, what I've got is a series of playlists. Some of these things are in development. For example, the basic electrical circuit analysis. If you look at the full playlist here, it consists of, let's say, a bunch of them. Not all of these things are on the electrical circuit analysis course. So 84 lectures in that first one, and they're sequential. So students assign a certain quantity of lectures. They do a worksheet. We come in, we discuss the worksheet face to face, and then we do the lab, and the structure repeats itself over an 11-week course. So the students enjoy the online lectures. Number one, they're capable of watching them asynchronously when they have the time to do so. Some of the students are capable of having full-time jobs, family responsibilities, and they're also capable of keeping their internships over the summer so they can watch these things asynchronously when they need them. Additionally, they're capable of revisiting and reviewing them for exams. So I'm actually going to switch over to all right, can y'all see this PowerPoint? Yes or no?
I cannot, Jim.
Okay, now,
Yeah.
okay, I gotta stop. I'm gonna stop the share. I'm gonna go back to a share and get to this one. Yes?
Yes.
Okay, cool.
Yes.
All right, so I'm gonna go ahead and switch to slide view here. One moment. Everything's in the way, 1 second. There we go. Okay, so as Andy stated, this is we're going to talk about is motor control, some of the resources I've been using, and I would do a real quick introduction to what the Electromechanical Technology Program is. It was based on an electrical engineering technology program a number of years ago, and around about 2005, there was an explosion of wind turbine development out here in the Gorge. It's kind of an area between Oregon and Washington. A lot of wind is coming through here. And so a lot of the wind turbine owners and operators came to the Columbia Gorge Community College and said, we like what you're doing with electrical engineering technology, but want to see if you can make a renewable energy technology program. And I was hired as part of that effort. And what we did was basically added on mechanics, hydraulics, motor control, programmable logic controllers, and safety. And we became the renewable energy technology program. Fast forward a couple of years later, there's a number of industries in the Gorge where not just wind turbines, we're not just hydropower. There's a growing avionics and advanced manufacturing and food and beverage processing out here. So we renamed ourselves the Electromechanical Technology Program. So again, it's all the same stuff. One of the things that historically students tell me upon graduation, the two most important courses that they've gotten here is motor control and PLCs. And so what I really am trying to do is make this course as we update, make the program, as we update the program, is to make motor control and PLCs a more centralized topic. And as you can see, where does motor control fit in here? It's in their first year of the third quarter. So students come into this with an understanding of DC circuit analysis, single phase AC circuit analysis, and they're concurrently taking Basic Electrical Circuits 3, which includes 3-phase AC circuit analysis. I have had students come into motor control with no understanding. However, they've had some previous mechanical or electrical experience. For example, some of the individuals that work at Full Sail Brewing or Google have come in and taken the motor control course and have never had issues. This being said, there are prerequisites being electrical circuit analysis 1, 2, and the concurrent taking of Basic Electrical Circuits 3. So what the course content for motor control is, it's an 11-week course. It really focuses on hardwired relay-based ladder logic. At the very end, we get into a very, very basic introduction to programmable logic controllers and motor control. So first off, we've got motor theory. I'll actually explain the course content piece by piece later. But the two resources I want to show you up there is the bottom one on the lower right is something called it used to be called LabVolt, but it's Festo. It's the 8036 Industrial Controls Trainer. So we actually have one of these things. It was funded by Caithness Energy. They're the individuals that own Shepherd's Flats Wind Farm, very, very close to us here. It's a great piece of equipment. What it is, it's contactors, overloads, relays on a pretty easy to use interface for the students. Allows a lot of visualization. You can put this in the thing in front of a class. What it lacks is the actual hands-on hardwiring experience of identifying terminal numbers and just identifying components. So it's as great as it is, it's a little plug and play. So that's why I adopted this thing in the upper right-hand corner. But what it is, it's basically a collection of very, very small, cheap motor control components consisting of contactors, overloads, relays, pilot lights, and push buttons that we can perform all the same experiments on that 8036 trainer, but the students get a little bit more hands-on actually wiring the circuits up. Additionally, it's maybe 1/64th the price of that, and the students actually get to use it. Okay, so the motor theory lectures, what these are is a basic understanding of motors, mechanical power, torque, rotational speed, rotational, the rotating magnetic field. And one of the key things I think the students need to understand is there's a whole family of motors out there. And what this course is really about is a squirrel cage induction motor. If you're to draw a motor family tree, where there's the DC, the single phase AC, and the three-phase AC. Three-phase AC has two branches, synchronous and induction motors. We're over in the induction motors. And inside that branch, you've got wound rotor induction motors and squirrel cage induction motors. That's where we're at, squirrel cage induction motors. So again, you need to understand that these are first-year students. That's the only exposure to the motor they get. Luckily enough, that's the most popular rotational actuator in the universe. So the squirrel cage induction motor is what we focus on for that quarter. When they come back for the second year, that's when I'm going to go into wound rotor induction motors. That's when we're going to talk about synchronous motors. One quick thing I'm going to show, I'm going to have to switch the share again. One moment. I'm going to go back to the website. And if you wanted to use some of these lectures here, what I'm talking about for that motor theory portion of it, if you go to the playlists, sorry, that's not playlist. Here's playlist. It's the motors and generators playlist. And that has all those lectures in there. For example, the motor family tree, mechanical power, rotating magnetic field, so on and so forth. As part of a new NSF ATE grant, I'm actually going to go ahead and continue working on this. I'm starting some new lectures with squirrel cage induction motors, followed up by wound rotor induction motors, permanent magnet synchronous motors, so on and so forth. So that first portion of that deals with that playlist. Again, that's motors and generators. Okay, now we're actually going to go into motor control. So that's the first week. Actually, one quick thing about that too, that motor theory also includes motor connection diagrams, and students get a chance to use the Megger MIT 410 installation tester, i.e. the Megger, basically to check motor winding installation. All right, the next portion deals with the motor control playlist. And I'm going to go back to that new share. Back to here. And this is the kit that I use here. So electromechanical components, we're starting off with this box of equipment here that a student gets on that first day. And we go through a very basic introduction of circuit breakers and fuses. We actually wire up a control transformer, learn to use a transformer connection diagram. What's a control relay? What's a normally closed contact versus a normally open contact? A manual motor starter, what's inside a manual motor starter? A contactor, how to read the terminal numbers, overloads, switches, all types of switches, pressure switches, temperature switches, rotational speed switches, float switches. What's a maintained contact versus a momentary contact? E-stops, adjustable overloads, how do you adjust it? Some of the old school overloads, I've got some examples of the ratchet style overloads that students may encounter. So the electromechanical components portion of it takes probably about a week for the students to get through. By the way, I should actually mention, historically, labs at Columbia Gorge Community College have been 1 3-hour session. What I've broken this thing up is to 2 1.5-hour sessions throughout a week. And I feel like the students get a little bit more out of the shorter lab experiences. So this might take 1 lab here of just going through the kit. The next section deals with ladder logic. And one of the most important things I think a student can understand in ladder logic is obviously the schematics, but also the concept of normally open versus normally closed, and the super, super important concept of normally open, held closed, normally closed being held open. Okay, so the ladder logic diagram that you're seeing right there is probably the ladder logic that they used back in the Roman days when they taught motor control hundreds of years ago. It's the classic float switch. The float switch is a normally closed float switch being held open. So I have done this lab in the past with a tank with a float switch in it. It's a really bad idea under Full Sail to have water inside an electrical circuits class with a bunch of students there. So what we do is just a simulator. It's a normally closed switch being held open. And when the liquid in that tank drains down, that normally closed switch goes back to its closed state and starts the alarm. So the students that's our first lab that we actually do wiring something up. It's a great experience for the students to actually get some hands-on experience with it. Another important thing that the students learn in this early lab is wire numbering. Any of you guys that worked in some really, really large industrial, for example, a wind turbine, there's hundreds and hundreds of wires there. If they're all the same color, it'd be impossible to find anything. Getting used to actually doing wire numbering and working with a partner too. Under COVID, I've been working as a single person, but I previously have had students work in pairs, which I actually like a lot better. They're capable of checking each other's work. Starting from one end of the rung, left to right, only on that rung. Move down the next rung. Left to right, work on that rung, move down a rung. So again, this is their first thing they've wired up. It's very important you as an instructor to go ahead and verify that they're hooking everything up. And I basically do a line by line check. So our next slide here talks about motor starters. Very, very important conceptual difference between 2-wire starters and 3-wire starters. I start them off with a 2-wire starter, a handoff auto, and then their classic 3-wire switch. One of the biggest things that I can talk about in this lab here is this concept of the overloads. When an overload is tripped, there's often 2 methods, an automatic reset or a manual reset. And the example I give them is a 2-wire circuit. In the event that that float switch is closed and it's in auto mode, if that motor overloads, the overload contact on the right, the normally closed overload on the right is going to open up and stop the motor, okay? However, if that float switch is still being triggered, when that overload cools and resets in auto mode, the motor will instantly start. So it's a very, very important concept for them to understand safety-wise. You need to actively lock out and tag out that system, okay? So now go over to the 3-wire circuit. In the event that that motor overloads, that normal closed overload on the right opens up and stops the motor, and the holding circuit drops out. If that overload was to cool, it would close, but the motor won't restart. So another important concept to understand is troubleshooting. What if this overload was not in an automatic reset, but it was a manual reset? Say that the motor has gone into an overload, and this normally closed overload contact opens up, stops the motor, and it's cooled, but it hasn't reset because it requires a manual intervention, a technician to come along and press that reset. So getting them early into this course to understand, number 1, safety, the difference between an auto and a manual, and number 2, troubleshooting, the difference between an auto and manual. The circuit may be functional, however, that normally closed overload is open. All right, so we're probably about week 3 or 4 in the course. Sometimes I teach motor starters with jogging. Sometimes I don't, but I'll go ahead and give them an exam at this point. So I have a tendency to do 3 exams. This motor starters with jogging, sometimes I put it in that first exam, sometimes I don't. Real quick introduction to this is the friction brakes and motor starters with jogging. And I'm going to go ahead and switch over my screen again to, if you haven't seen it before, one second. There we go. Okay, this is the piece of equipment I was talking about earlier. This is the Laval 8036 industrial controls trainer. And what it consists of is those exact same things that you've dealt with previously, only this time they're in this kind of this sexy lab bolt / Festo mock-up here. Let's say you've got your coil signal A1 to A2 right here on the actual contactor or a relay. But what they've done is drop those out here so a student can plug and play. So it's much quicker than an actual hands-on lab. However, the students aren't really getting that the practice of wiring up. But what I do like using this system for is a rather quick demonstration. The motor starters with jogging, there's several ways to create a jogging circuit. And that's why I introduced them to this. I have a couple student groups go up in front. It's double-sided so they can work together, but it's nice to see 4 or 5 different implementations of a jogging motor starter. The other thing I could say about this, there's a friction brake on here. So it is a spring-held, electrically released brake. So it's always a great thing to show them, okay, what happens in a locked rotor condition when the brake fails to release? Obviously, the motor goes into an overload. So troubleshooting a scenario with that. This is a great way to introduce that piece of equipment. You don't necessarily need this piece of equipment, but that's the first time I actually use it. Okay, so that's the motor starters with jogging. The next subject is reversing motor starters. So up to this point, what I've done with the labs historically is do a line-by-line verification with the students. Now there are 3 or 4 or 5 or 6 labs into doing this. This is the first lab where I'm going to let them wire everything from the beginning to the end. Sometimes it's successful, sometimes it isn't. Obviously, before you go ahead and let them go to run the circuit, you actually go ahead and verify everything. But I let them go from the beginning to the end. Now they've got some good wiring practices. They understand wiring numbers. They're capable of working with their partners, and I just let it run. So super important about this, which I should have mentioned earlier, part of that kit includes a plug cover, so a locking plug cover. Obviously, in a lockout and tagout environment, 2 students working together, they each have their own keys. In an industrial environment, don't do that. Have one set of keys and you have the keys. Very, very important to keep the students from plugging it in. And before you plug it in, you verify it and you unlock it. Okay, the next concept is reduced voltage starters. I have a tendency to blaze through this one and only perform 2 of these labs. This being said, if you wanted to do all these labs, that option is available. Obviously a Y-star delta run, you're going to have to grab another contactor in that kit. Timer applications is our next setup. And this is where we kind of get into some really cool applications. I think one of the most fun applications is the plug to stop. Actually get so plugging, by the way, if those that are not familiar with it, is the instantaneous reversal of the rotating magnetic field. And what happens is if the motor is rolling forward and you open up the forward contactor and close the reversing contactor, the motor will decelerate and then begin in the rotation in the opposite direction. Obviously, sometimes you don't want that to happen. But in this case, what we're trying to do is we're going to try to plug it to stop it. So the student will basically get the motor rolling in one direction, we'll plug it and adjust the timer such that the motor comes to a complete stop. So that's a really fun one. Some of the times the students get it right on, sometimes they don't. Now, moving on to the next subject is a very, very, very basic introduction to programmable logic controllers. Like I said, the 2 courses that students recognize as being the most important is motor control and programmable logic controllers. I'm trying to give them an introduction to what they're going to do next year and how that motor control directly relates to programmable logic controllers. So I don't use a full-on Allen Bradley for this one. I use a couple different styles of very, very basic, simple programmable logic controllers. The lower one on the left there, that's the Chico SG2 PLR. That's about $100. So very, very, very cheap, very inexpensive. It is a free software and you get what you pay for the software. So it's not exactly the best software, but it gets the job done. You guys might have seen this, the one in the middle, the Siemens logo that is used very extensively in the Bonneville Power Administration, U.S. Army Corps of Engineers out here for a number of the dams in the Columbia River. It's a little bit more expensive, $120. And then the one on the right is the Eaton Easy PLR. That is a great piece of equipment. This software is much, much better than all the others. Great simulation utility. However, it's discontinued. So I'm kind of heartbroken about that. The Allen Bradley also used the Pico microcontrollers. Those have been discontinued also. So we're kind of up in the air right now. We're going to stick with the Tico SGT-PLR. One of the important things about programmable logic controllers is this concept of interface methods. And I try to get them to understand really quickly about safety. So what I've drawn on the left-hand side here is a very, very, very simple ladder logic diagram showing 3 inputs disappearing into a PLC. That's input 1, 2, and 3. And then 1 output coming out of the PLC. That's Q1. Okay, there's a fundamental difference. Before I go on to the explanation, there's a fundamental difference. Let me slide this over. Before going with the explanation, F1, that's a normally open auxiliary contact associated with the F contactor. When the F contactor is closed, the motor starts turning, but additionally, F1 auxiliary contact closes. And what that is, it's an actual physical real world feedback for the PLC to know that this motor starter, that the contactor is closed and the motor is running. Okay, so that's a very important point there, is input 3 is a feedback. The system is running or the system is not running. Okay, the second point I like to make about this is the E-stop on the left-hand side. The E-stop kills all power to all inputs and to all outputs. All right, you guys have all seen the Terminator movie before. Okay, the punchline of the Terminator is never trust a machine. Always have a way to kill it. And that is my personal preference, is to have an E-stop on all inputs and all outputs on a PLC. Even if the program is calling for an output to be asserted, you can kill that output with an E-stop. Obviously, this is not the case for all scenarios, but I try to get students thinking about this earlier, very early in their career. You need to have a way to kill a machine at any point. You always have to have an E-stop to kill inputs and outputs. The third point I like to make about that diagram on the left is the normally closed overload contact on the far right-hand side in series with the F contactor coil. You must wire the overload contact in series with the F contactor. And the reason why is this: the overload has the last say whether the F contactor coil is energized or not. Even if Q1 output of the PLC is closed, if that overload is open, the F contactor coil will not be energized and the F contactor will not close. Okay, and the important point I'd like to make about that is very evident on the 2 diagrams on the far right-hand side. The top ladder logic diagram is a software-generated holding instruction. And allow me to just go on my soapbox here. A lot of, I guess, pre-made labs that you'll see about programmable logic controllers that you find on the web, or you find at a manufacturer's website, or you find, for example, Festo or LabVolt, they're going to use a software-generated holding instruction, where when Q1 output is asserted, the Q1 make contact closes or allows logical continuity. If you use that in the field, you will kill someone. Okay, that is, you cannot use that. And the reason why is this: for the system on the left here, if that normally closed overload contact, let's say the motor's running, the normally closed overload contact opens up, the motor stops. However, the logical output Q1 is still being asserted by the programmable logic controller. And when that normally closed overload contact cools and resets, if it's in auto mode, the motor will instantly start and you will kill someone. Okay, there's a much, much better, much safer way, and what is done in the field. I much prefer individuals to use what they're going to see in the field is to actually use real world feedback. Where is the real world field feedback? It's on input 3. That's the F1 auxiliary contact associated with the F contactor. You must have an understanding if that contactor is open or closed. So the motor starts, F contactor closes. Let's say the motor overloads. If the motor overloads, the F1 contact opens and removes the holding circuit. So you're getting that real world feedback. So when this overload contact cools, the motor's not going to restart because the removal of the holding circuit based on real world input. So it's a very, very important distinction for students to understand those software generated holding instructions versus real world feedback. And I will say historically, a lot of textbooks, a lot of pre-made labs out there do not do a good job of explaining that. All right, I'm off my soapbox now. All right, motor drives. Last but not least, the motor control course ends with a very, very, very brief introduction to motor drives. The one on the top is what I've been using for the past couple of years, is an Omron 3G3MX. It's a we use a little quarter horsepower motor drives, very, very inexpensive motor drive. I'm not certain if you guys are aware, we experienced a really, really bad flood here in Columbia Gorge. Our labs are destroyed. I don't know if you can see behind me, but our labs are kind of destroyed. Some of these motor drives got destroyed with it. So we're actually thinking about upgrading the PowerFlex, the Allen Bradley PowerFlex 525. And the idea is to use those not only in motor control, but also in the later programmable logic controller class. We're going to expand it to include networked drives. What I do in motor control is very, very simple. We're going to install a motor drive. Well, number one, we're going to look at the motor drive, look at the data sheet, learn its pin outs and pin ins. A very basic understanding of volts per hertz control, because obviously at lower excitation frequencies, that inductive reactance is very low and the impedance is very low. So you're going to have to drop your voltage down so current doesn't go too high. But as that motor drive ramps up, not only are you increasing frequency, you're also increasing voltage. We're going to talk about acceleration and deceleration control. This particular motor drive actually does DC injection braking, which is super cool. Students get to see that at the get-go first year. Obviously, motor drive protection mechanisms, how to adjust for an overload on that motor drive. And last but not least, I think one of the biggest things for a student to understand is direct versus remote operation. So they're actually, up to this point, have been actually operating the motor drive on its face panel. Now we're going to go ahead and take these inputs, for example, a remote speed potentiometer, a start and a stop button, a jog button, and we can do several labs at once with a motor drive. One thing I should back up about programmable logic controllers, student up to this point has been maybe 8 weeks in the course, maybe 9 weeks in the course, and the programmable logic controllers section, once we introduce that, we wire up the programmable logic controllers and do 5 labs in one day. We do a 2-wire, we do a 3-wire, we do a jogging, we do a reversing, so on and so forth. Same thing with the motor drive. There's programmable operations we can do. We do 5 or 6 different iterations of that all at once. So that really concludes the presentation as far as what I've got. Let me go ahead and stop the share. I'm back here. And so I've got the opportunity to answer some questions. I've got some cool stuff I can show off right here. I don't know if there's any other things that you need to know about this. Before we open it up to questions, I wanted to show this real quick. I have, in addition to the motor and generator playlist and the actual motor control playlist, I also have a programmable logic controller playlist. And it shows how to build a very, very inexpensive PLC trainer, which I'll show in a moment once I stop the share. This playlist is in development right now as part of the new NSF ATE grant. I'm actually going to be producing more content for this, and including some digital logic. So stick around for that. And the next one is, everything's on top of the screen. One moment. There we go, motor drives. And that's this full playlist right here. So that is the lecture. I don't use all those lectures for the motor drives, because some of them are pretty specific, but I obviously talk about introduction to motor drives, direct operation, volts per hertz control, and deceleration and protection methods. Stop the share. There we go. And so one of the tools I was going to show you is, this is something, an idea I experimented with a couple of years ago. Our digital logic class is taught using a field programmable gate array, an older TTL technology. Long story short, the students never use TTL, and no one gets a job programming field programmable gate arrays out here. What they get a job is working on PLCs. So one of the ideas I thought about is, rather than using this technology that's outdated or not used, is to teach the PLCs, teach the digital class using something like this. It's an Eaton Easy PLR with a couple push buttons on top, a couple lights on the bottom. This would cost maybe 180 bucks, let's say $200. Basically the price of a textbook. The idea was to have a student buy this equipment. We wire it up on the first day. They take this thing home. They do all their labs on it, and they actually get to take this home. This idea has kind of died now that Eaton is no longer manufacturing this one. However, you could easily find something equivalent like a Siemens logo or the Chico SG2 PLR. So this is another piece of equipment that I've been experimenting with. I think we may end up actually upgrading our programmable electric controllers to the a newer type. We might use that, but that's something you might see. Another inexpensive option for motor drives, some of you may or may not have access to three-phase AC. We've got drop connections in our lab. There also exists the Chico FM50. It's a single-phase AC motor drive, very, very, very inexpensive. We use these things when we were in a different lab, but now we've got three-phase AC. We could actually use the real deal. This is the really inexpensive quarter horsepower motor we've been using. One of the things I've found is with students, very similar to soldiers, give them a rubber hammer and an anvil. If you come back in 5 minutes, they'll have broken both of them. So what we've done is taken the terminals from the motor actually to a terminal block. So keeping them out of here, and they can actually wire it up, and in Y configuration, high voltage or low voltage, they can check the insulation winding resistance. So keeping them out of actually touching the wires and using the terminal blocks. This is a kit right here. And one of the consumables that you'll find is for a reversing motor starter is using a reversing wire kit and then a mechanical interlock. This thing costs about $17. They always come back broken, so it's great to just have a student buy those. Having a student purchase their own set of wire numbers, this is great use of their actual student funds. And last but not least, the actual motor controls trainer itself. All it is, it's a metal backing here with a bunch of wire ducting on it. The circuit breaker and controls transformer remain mounted on it. The programmable logic controller also remains mounted on it. And like I said earlier about the motor, I don't like students having them touch having them actually wire up the programmable logic controller because it's very, very small screws. So what I've done is taken all those inputs to the outside to terminal blocks, so they actually can interface with the terminal blocks, a 15-cent terminal block, as opposed to an $80 programmable logic controller. That is all I've got right there. This is the locking plug right there. All right, so I got one question I just popped up. What is it? Do you have, oh yeah, so that is actually a great question. Do you have a bill of materials for your kit? So Gabby has sent you, or should have, has not, maybe has not yet, but she has a parts list for this. Everything I've purchased is from Automation Direct, with the exception of the motor drives and the actual motors themselves. And I want to say the kit costs, if you was to purchase at retail, it was about $400. Obviously, with the slow motion collapse of society here, everything is taking a lot longer to get to you, and things are out and things are expensive. So things have, obviously, prices have increased, but That being said, Automation Direct does give educators a 20% discount. So I would definitely check those out.
Hey, Jim, this is
yes,
Gabby here.
yes.
And I will get the list out to everybody on the call this afternoon. So
Awesome.
plan on sending it out after the webinar.
Yeah, so what I'm saying about the online resources, feel free to make use of those, not only for the motor control class, but the electrical circuit analysis classes, the hydraulics. I got some pneumatics materials coming up. I got some more motors and generator material coming up. And feel free to skip around too. If you don't want to talk about Thevenin's theorem, don't talk about Thevenin's theorem. Move on. You can mix and match those things as you see fit. The other thing is I'm actually producing some study guides for those. Stay in touch with those because it's going to take a while for it. And I've actually had some folks at Ann Arundel Community Colleges, specifically Tim Callahan. He has actually adopted the motor control, the entire motor control series, and he's been doing it with his students. I want to say it was last quarter. I actually got to get in touch with the guy to see how it went. So feel free to make use of this equipment that I'm using and those lectures. All right, I think that's really all I got from my portion of this here. I did want to open it up for questions.
Yeah, Jim, that was great. I just want to chime in and again say that let's open it up. If anybody has questions, please feel free to ask. I have a couple here that I'm happy to ask if we don't get any takers. So I guess, Jim, one thing, if you could tell folks a little bit more about, and you mentioned this some, but maybe go in a little bit more depth about the type of content you expect to be making with this upcoming NSF grant, right? So you, you mentioned some, but
yeah, so the first NSF grant was largely focused on our first year content, electrical circuit analysis 1, 2, and 3, DC, single phase, and 3-phase AC. We teach on an algebraic basis, i.e. non-calculus. I also develop content for hydraulics and motor control. What's missing there is our mechanics course. I don't teach the mechanics course. It's kind of hard to teach mechanics online. So we're going to keep that as a face-to-face class. There is some hybrid stuff that the instructor's doing. So we're not going to do that. You might see some of that. The missing component is pneumatics. So the thing I failed to do on the last NSF ATE grant is the pneumatics content. So that's coming up real soon. I'm starting to produce some pneumatics content. And, you know, again, my background is industrial wind power because I kind of made fun of pneumatics because they're cheap and light and weak. But what's great is they're cheap, they're light, and they're weak. And it's a great way of teaching, I guess, PLC concepts, as opposed to having just lights that go on and off, actually having actuators that go out. You can time them, you can count them. So I'm actually becoming a bit of a pneumatics nerd lately. They're clean. It's nice. You're going to use the hall in the center here for a pneumatics lab. So that's coming out. The other thing is the second year content. There's a huge hole in our power generation and transmission class. Like I said, I'm going to be going into induction motors, synchronous motors, wound rotor induction motors, permanent magnet synchronous motors. I'm going to DC motors. The only reason I might do single phase AC. I don't like single phase AC motors, but sometimes you got to get used to them. So pneumatics, motors, and generators. And then following that, what I'm actually going to try to do is some power electronics, rectifiers, inverters, thyristors, IGBTs, and then most of the rest of the grant will probably be spent on industrial wind power and solar power. And I will be so bold as to make use of all the stuff that Ken has already put out there. Some great resources that create. Definitely appreciate some of those too. So yeah, that's what's coming your way. Unfortunately, we had a little bit of disaster here at CGCC as far as the flood goes. So it's not coming out synchronously. I'm not just going to be doing motors from the beginning to the end in a logical sequence. So you may see me jump around a bit, but after 3 or 4 years, I'm hoping everything out there.
Nice.
Yeah.
Thanks. So I have another question from somebody, and it was more of a kind of a practical question about being in the lab. And the question is, different variable speed frequency drives have different noises and sounds they produce. And have you ever had a class full of students running all of these at the same time? And does the noise get to be to the point where it is distracting or just unbearable?
Yeah, it was. I think it's ironic because we've actually had all the acoustic tiles got destroyed in this flood here, and they actually pulled the acoustic tiles out. I'm like, I think we're going to need those back. These particular drives don't particularly bother me. I think they're switching at 16 kilohertz. If I can't, and you know, some people lose their hearing around 20 kilohertz. I had one student who was seriously hearing something at 21 kilohertz. I mean, the guy was like, he was a high school student, or Washington has the Running Start program. He was 17 years old, but he could hear at 21 kilohertz. And I did test him and he could hear it. So yeah, I personally have never been bothered by it, but I wonder if I survey the students if they've been bothered by it.
That's interesting. So I guess I have another question as well, as far as kind of when you have students doing the online lecture and then they're coming to campus for lab. I mean, I know that obviously with the pandemic, everything was different, but even prior to the pandemic, or now that things are going kind of back to being more comfortable in classrooms, do you have students asking, hey, Jim, can you we want to do it all online. Can you send us this? Or do you think that the students do like the kind of that mixture of being able to do the lectures online, but still having that kind of classroom experience and learning opportunity with you in person, with their classmates in that piece? Or do you feel that, I guess I'd just be interested to know your thoughts on the trends of what students like.
Yeah, there's something to be said for exporting exercises to students. That being said, this thing I would be very, very uncomfortable letting a student even wiring up a single phase AC, because it requires some guidance for this. You know, that the lab is there to be a safe and supportive environment with the guidance of an instructor. There are certain classes, however. For example, some of the content I'm going to be developing in the new NSF ATE grant deals with protective relaying. And I think that's something that I can export to the student. It's very expensive equipment, and we do have some of the equipment here in lab. What I'm going to do is have some take-home exercises for the protective relaying. Another classic example is I've got a battery data sheet reading exercise that I use from a power generation transmission class. And you guys, we're kind of in an area which gets some pretty rough snowstorms. And I guarantee every year we're going to have a snowstorm that shuts the school down. And we have this great notification system at Columbia Gorge Community College about snowstorms. They wait till everybody gets to class and then they cancel school. So what I do is I always have this battery data sheet reading exercise. As long as a student has series DC circuit analysis, I can pull this thing out and say, you need to take this thing home and do this now. So that's a great exercise that I can export out there. And I think as time goes through, I'm going to identify more and more things that you could push out to the students, and then those things that you need to keep in-house. And I think the major advantage, I mean, think about it, society is moving on here. Everything's moving virtual. Education can be pushed out virtual, but what do community colleges have? They have access to the expensive real world equipment, and that's what students are paying for. They're paying to use this equipment and the guidance of an instructor, and they do actually like working with each other sometimes.
Yeah. Nice. I guess I'll throw it out there. Does anybody else have any other questions that they would like to, I believe Gabby has turned off or enabled your ability to turn your microphones back on if you're more comfortable asking a question verbally as opposed to written. With that said, I could continue to ask you questions, Jim. So I'll ask you one more. And it's more, it's broader than this specific topic and more about the impact that you've had with BigBadTech. So I have noticed, and I'm sure that any educator who is watching this or will watch this will be pretty amazed at some of those videos, the video watch count on some of them. And I'm just curious whether or not you have whether or not you have insight on how that has happened, or if it's just been this thing that you released into the world and you look at it as just as amazed as anyone.
Well, yeah,
I'm sure you've done.
Yeah. So the whole origin of this thing was I was teaching DC circuit analysis. Very end of the quarter was Thevenin's theorem, and I was teaching face-to-face at the time. Thevenin's theorem is, it's not that hard, but it requires some repeat exposure to it. So I was teaching a class of 32 students, taught Thevenin's theorem. At the end of the day, maybe 24 of them got it, 8 didn't. So for us to move into that lab, I had to go ahead and reteach Thevenin's theorem the next day. And out of those 32, maybe 8 more got it. Excuse me, 4 more got it. So I got 4 guys that are still out there struggling with it. And I said, listen, I can't waste no more class time on Thevenin's theorem. I'm gonna make a video of just Thevenin's theorem examples. I'm gonna put it on the web. You need to go home this weekend, knock out all those examples. And you show up on Monday, you need to be ready to roll. So I put this lecture out there. It was up to 20,000 hits on just one lecture over the weekend. And it's not because I'm the best. It was because I'm the first, you know, like I was one of the first people to do this. It was like 2008. It had a crappy, a really awful microphone, but people love this stuff. It was just an example problem. So I started doing more and more of that. And I ended up developing a digital logic series at Columbia Gorge Community College live. That was based on TTL. It was kind of older technology. I redid it to include field programmable gate arrays. And that's when I met y'all at the Australia thing? Was it 2014 or 15?
Australia, yes.
Yeah, so Dr. Kathy Alfano, who used to run Create, she was like, hey, would you ever consider doing this for electrical circuit analysis? And I said, yeah. So I started doing this and on this own channel. And so, and all the graffiti thing that was actually a failed NSF project that I originally proposed that I kept all the stuff for. So I kept going with it. And yeah, it's funny to see the explosion of interest. You know, I've had offers of marriage on some of these things here too. And obviously there's some cranks out there that hate me for, you know, they're just sour about education, whatever. But for the most part, I've received incredible thanks for this. If there is an error, because obviously there are errors in it, what I try to do is I try to catch it. And if you catch an error in there, let me know, and I'll put in those, the very top of it, I can tell where the errors are. And what I found too, when I've done this is I initially made an hour-long lecture, let's say about hydraulic math calculations. And I did everything. That's not the way to do it. So I've been going back and redoing some of these things. For example, the DC math, I'm talking about I'm talking about engineering format. Then I'm going to talk about algebraic manipulation. Then I'm going to talk unit conversion. So I've got these conceptual lectures now, but now I'm also including these example problems lectures. A student can actually pause the lecture, try the example or problem themselves. And when the answers flash back up on the screen, if they got the answers, they move on. If they don't have the answers there, rather than a textbook static explanation of it, you got me walking through them, the steps and the most efficient way to accomplish that. So that's what that's kind of the history of it.
Yeah, no, as someone who has, I cannot claim to have watched all of your videos, Jim, but I have watched several of them, and I have seen some of those. You can almost see those iterations of advancement in trying to deliver not just lecture, but educational experience to students by doing those types of things. I think it really does show in those videos. So one other thing about that. So have you seen, are these a good recruiting tool, would you say? I mean, have you had students come enroll in your courses that say, I first learned about you from BigBadTech, or is that kind of, it's almost two different worlds? There's the online delivery of the lecture world, and then there's your kind of local student body of potential students.
Yeah, totally. No, I've had a number of students come to our program specifically looking for this content. And I can't remember what year it was. It was high tech when it was in Portland, 2015 or whatever. And I had my little name tag on. I'm walking through the hall, and this dude stops me. He's like, "You're Jim Pytel. I use your stuff all the time." And I guess he was some diesel mechanic, but he was teaching the hydraulics courses for diesel mechanics in Yuma, Arizona. And I thought it was pretty cool. So it sounds like what I saw a comment is Graham, as I guess he's been using. Yeah, okay, cool. No, I'm glad that you've been using it. Yeah, like I said too, it is, feel free to mix and match some of those things. For example, this is how I went through school: electrical circuit analysis, needs to have DC, single phase AC, three-phase AC, and it needs to discuss phasers, okay? Very, very important math to understand. If you don't like that stuff, and if you don't like some of the theorems like Thevenin's theorem and superposition theorem, you can skip some of that stuff. So I think that's the other advantage. So Glenn, I'm presuming you're using some of that, but not all of it. And so feel free to use these things as you see fit. And obviously with the understanding there may be some preceding material that you may or may not. If you want the whole experience, I'd recommend the whole thing, but you can skip around in these. And so Glenn, which classes are you using the material for? I don't know if it's...
I've been using them for a variety of classes, and I choose those videos that serve the course outline and record best for each class.
Nice. Is it electrical circuit analysis or?
Well, I teach classes in primarily in electronics, but I also started an electrical program at our college, which has been a real success. And we actually have more students enrolled in the electrical now than in the electronics. And I cherry pick. I go in and I find those topics that best suit the topic of the day for each class.
Nice. One thing going along that too is another thing that you may find as an instructor is sometimes a student, you can tell them the same way 4 or 5 times. They're just not going to get your particular description of something. You feel free to use these as alternate resources. Let's say they're having a problem with the voltage divider rule. You don't explain the voltage divider rule to them 15 times. They're not going to understand it. Hey, check out this guy. He's got another way of teaching it. There you go. And so hopefully you guys can use these, not if they're not taking place in your classes or your textbook, you can use them to supplement it. And also to riff off that is I'm not using a textbook anymore. There is no textbook associated with this class. All the students have is the lectures and study guides and worksheets that I give them. This being said, I do have an optional textbook if they want it. No one buys it because they don't need it.
Yeah, Jim, the robustness of the way that you've delivered this content really is, I think, to your point, is it can fit kind of whatever need the instructor has, which is quite nice because, again, you're going to have a whole spectrum of folks and how they want to use them or need to use them or use them primary or secondary resource. It's great.
Very nice. Thank you, guys.
This was fantastic. If there are no other questions, I think we've come about to the end of the hour, but I'll give one last chance for questions or comments or thoughts. But otherwise, Jim, thank you so much for your time.
Awesome.
If you have any closing remarks, you're certainly welcome to have them. And if not, we can adjourn.
Yeah, come on and visit, guys. We're out in the, you've been here, right, Andy? I know Ken has.
I have.
Yeah. Come on out, guys. We got well, not this week because we're doing construction here. But yeah, if you guys want to come on out, we've got wind farms out here that we've got really good connections with. The other super exciting thing that's going on right in our backyard is the new Goldendale energy storage project. It's an older aluminum plant that they're at the very bottom of a hill right next to Columbia. And they're going to pump water up to the top of the hill when there's sun and wind. And when there's no sun and wind, they're going to let it drop and generate. So that's going to be probably this summer when it's going to be starting construction. Highly recommend you guys coming out for that. I know Blanche and Ken Scheinkoff, who are my evaluators from the NSF ATE. I'm trying to keep them in touch with that because we're going to be doing a site tour.
Yeah, that's been a project long time coming. I know we discussed that project many years ago. So that's great to hear that.
Yeah, it's finally happening. Yeah.
Oh,
Thank you so much, Jim.
Thanks, guys.
This is Gabby here, and I just wanted to let everyone know that I will have this webinar, the recording of it posted up on the Create website in about a week, and I will send out an email to everyone, and that we have another webinar coming up on March 4th, so you guys will get an email about that, and we would love to have you guys join us for that too.
One quick thing here. I just noticed something on the chat that Glenn said the ADA. So actually leave a physical space on the bottom of the lecture. Is that what you're talking about?
Yeah, the problem is that I'm required on any video I show in my class to comply with ADA. And so I take your lectures and I put closed captions in a spot on the bottom, but I notice a lot of times there's not a free space. I have to.
Yeah, so it overlaps the actual lecture. No, that's actually a good point, because what I could do is like maybe, because I'm getting a new computer. The problem is my computer screen is so small. No, that's actually a good idea, because now I'm gonna have a bigger screen. Just not use that bottom, quarter inch, half inch or something like that.
Right. It could be on top or on bottom, because I can move them from top to bottom as needed. And I often do that. When you're writing at the top, I move it to the bottom. When you're writing on the bottom, I move it to the top. But in the meantime, it's covering up valuable information.
Yeah, no, that's actually a great idea, because what I can do is the utility I use is Camtasia, and I can, you know, I'll figure it out. Yeah, I could restrict that section from not recording and then just put like a white block in the actual heading. Yeah, because YouTube has done historically, it was kind of rough, especially for technical subjects. The actual transcriptions were a little weird. They've gotten much better. But then some college in Texas, I can't remember what it was, they actually wanted to put the captions in there. And a number of those lectures are not auto captions, but actually professionally captioned. And all it takes is somebody to just give me the transcript, and I just put it in there, and YouTube does the rest. But no, that's actually a great idea, putting just a space in the bottom.
Yeah, I spend about 4 or 5 times the duration of each lecture that I use just putting closed captions on these things. And it would be really nice if I didn't have to cover up your valuable material in order for students to have that advantage.
Well, it's also too, because we, a number of students out here speak English as a second language. So what they actually do is run the captions while it's going too. They do speak English, but they're using the captions to see it. Plus also, I mean, folks that are internationally using this thing too. That's actually great. I'm on it, man. Next couple, I've got a bunch of lectures already recorded, but once I start doing new ones, yeah, I'm gonna add that in there. That's cool.
Very good. Thank you.
Yeah, rock and roll.
All right. Thank you, everyone. We appreciate you joining us today, and hopefully we'll see you on our next webinar. Thank you, Jim.
Hi, again, Andy, Deborah, it's great to see y'all.
Have a great one.
See ya.
Bye.
Bye.
Hi, Jim. Thanks again. Have a good afternoon.
All right, rock and roll. Hey, Gabby, Andy, thanks for the intro, man. That was awesome.
Yeah, I appreciate that. Yeah, it's so funny that like all of a sudden I feel like I'm like, oh God, everyone's listening. Now I get get in my head and I'm like, oh, I practiced this a couple times a few minutes ago.
I got my notes, and I had my notes at the get-go. I'm like looking around, I'm like, I can't even find my notes.